Hello students, today we will discuss on two important points. First is the methods of structure elucidation of terpenoids and second is a very important compound citral. General methods of structure elucidation. First of all, we determine the molecular formula of the compound by means of mass spectrometry and molecular weight determination. If the terpenoid is optically active, its specific rotation can be measured. The second point is the nature of oxygen atom present. If the oxygenated products of terpenoids are taken, then we find the functional nature of the oxygen atom, which can be alcohol, aldehyde, ketone or carboxylic groups. Presence of hydroxyl group. If the oxygen atom is present in the form of hydroxyl groups, they can be determined by the reaction with acetic anhydrides forming acetates and with 3,5-dinitrobenzoyl chloride yielding the derivative. If the oxygen is present in the form of carbonyl group, then it is reacted with the hydroxylamine yielding oxime or phenylhydrazine giving phenylhydrazone or sodium bisulfite giving sodium bisulfite derivative. Third is if unsaturation is present in terpenoids, the presence of olefinic double bond is confirmed by means of the addition of bromine and the number of double bonds is determined by analysis of the bromide or by quantitative hydrogenation. Presence of double bond is also confirmed by means of catalytic hydrogenation or addition of halogen acids. Number of moles of hydrogen halide absorbed by one molecule is equal to the number of double bonds present in the terpenoid. Addition of nitrosyl chloride, that is Tyndall's reagent, and epoxide formation also gives the idea about the double bond present in the terpenoid molecule. Here is the nitrosyl chloride addition and here the per acid if taken, epoxidation of double bond takes place. Next is the dehydrogenation. On dehydrogenation with sulfur, selenium, platinum or palladium, terpenoids are converted into aromatic compounds as for example alpha terpineol. On selenium dehydrogenation yields paracymene, which gives the skeleton structure and position of side chain in the terpenoids. Next is the oxidative degradation. It has been the parallel tool for elucidating the structure of terpenoids. Reagents are ozone, acid, neutral or alkaline, potassium permanganate, chromic acid, sodium hypochromite, osmium tetraoxide, nitric acid, lead tetraacetate and peroxy acids. Since oxidizing agents are selective depending on the particular group to be oxidized, the oxidizing agent is chosen with the help of structure of degradation products. Relation between the general formula of the compound and type of compounds. As for example, limonene absorbs two molecules of hydrogen to give tetrahydrolimonene. Its formula is C10H20 corresponding to the general formula CnH2n. It means that limonene has a monocyclic structure. In this way, we can also determine the structures of acyclic, monocyclic, bicyclic, tricyclic and tetracyclic compounds. Last are the spectroscopic studies, which is the latest technique in which we involve UV spectroscopy, which gives the position of conjugated dienes or alpha beta unsaturated ketones. IR spectroscopy dealing with detecting the functional group present in the molecule, and NMR, mass and X-ray analysis is also used to determine the structure of terpenoids. Next we come to a very important compound of terpenoid, citral, which is the lemongrass. It is the most important member of acyclic monoterpenoid. Its chemical formula is C10H16, boiling point 77 degrees centigrade. It is found to have two double bonds which can be repelled by the addition of, it adds on two molecules of bromine giving tetrabromo product and 2 moles of hydrogen yielding C20H20 oxygen. That means two double bonds are present in the molecule. It contains 10 carbon atoms, which means 2 isoprene units are joined in the molecule, and an aldehydic group is present in citral. Now let us determine the structure of citral. First is the formation of oxime. Citral reacts with hydroxylamine yielding an oxime. Here spelling is mistake, OXIME, indicating the presence of an oxo group in citral. Citral, when heated with potassium hydrogen sulfate, it yields paracymene, which gives the skeletal structure of citral. On reduction with sodium and alcohol, it gives alcohol known as geraniol. In this, aldehydic group is converted into alcoholic group. Citral forms both mono and disulfides by the addition of sodium bisulfite to reveal the presence of conjugated aldehydic group present in citral. Citral, on reduction with sodium amalgam, it gives an alcohol geraniol. Citral, on oxidation with alkaline KMnO4, yields acetone, oxalic acid and labulinic acid. Here you can see how the oxidation takes place. First of all, it reacts with potassium permanganate, where when hydroxylation takes place, and then chromic acid oxidation. Here the bonding, the cleavage takes place from here and here, yielding acetone and oxalic acid plus labulinic acid. Citral, on oxidation with silver oxide, forms geranic acid, suggesting that citral has an aldehydic group present. So aldehydic group converts into carboxylic group. Based on the above data and coupled with biogenic considerations, citrals is formed by the joining of two isoprene units in the head to tail fashion. Structure of citral was assigned tentatively. The structure was further supported by the degradation of citral, which on treatment with aqueous potassium carbonate, it forms acetaldehyde and 6-methyl heptene 5-ene-2-one. The structure of citral is finally confirmed by its synthesis, which was given by Barbier and Buveldt. It converted methyl heptanol into geranic ester by using Refer-Mitzi reaction. After this, Tiemann converted geranic ester into citral by distilling a mixture of calcium salts of geranic and formic acids. Thank you.